Hello, guys. Welcome to the live. Can someone confirm if you're able to hear me and see me? Is the audio and video okay? Just give me a confirmation in the chat. Okay, let us get cool. So let us get started. Today's live session is about linked lists. In the previous sessions, we have been talking about arrays. I think we talked about arrays and we talked about binary search, two pointer approach, sliding window approach, and some other questions related to strings. Today we will move from arrays to linked list, and linked list is the second data structure that we are learning. And we're not going to talk too much about the theory of linked list. I've covered that in the live classes for all the students who are joining from my live classes. Otherwise, there is a detailed video on linked list that I have uploaded on my channel on the Breakthrough DSA playlist. So we have done arrays. My screen is not visible again. 1 second. Okay, we have done arrays, and now we are moving from arrays to linked list. So today's agenda is that we will solve two or three questions on linked list, some lead code questions. So when we talk about linked list, um, let us not do any theory of linked list. Let us directly jump into the questions. Okay. So let me go to the DSA sheet here, and here you can see that I have listed down a few basic questions on linked list. I think there are some 20 questions maybe on linked list. Let me see how many are there. Okay, there are some 25 questions on linked list. If you solve maybe 15 of them, I think you will get a good understanding of how to work with linked list. And in the live classes, I think we have done question number 71, 206, 876, and 21. I think these three questions we have done. We will try to revise one of them, but let us do some new questions. So let us start with question number 141. Okay. So let me go to question 141. It's an easy question. It is about linked list cycle. So let us read the question and then we will discuss the approach. Okay, everyone with me, guys? Tell me in the chat, please. Okay. So this question talks about linked list cycle. So I think when we were talking about linked list, I talked about circular linked list. So a circular linked list is a linked list where the tail of the linked list points back to the head. Okay, and this is a general circular linked list, but it is also possible that any the tail node might point to any other node also, and this question is a general question on that concept. Let us read the question and then we will talk about what is needed to be done. So it says, given head of a linked list, determine if the linked list has a cycle in it. Okay, so then there's a definition for cycle. So let us read that. It says there is a cycle in a linked list if there is some node in the list that can be reached again by continuously following the next pointer. Internally, the POS is used to denote the index of the node that the tail's next pointer is connected to. Note that POS is not passed as a parameter. Return true if there is a cycle in the linked list, otherwise return false. So basically what it is saying is that you have a linked list like this. Okay, and there is normally there is only one way to reach a linked list, reach a particular node in a linked list. That is, if you are on the predecessor node and you go to the next pointer, you reach a node. But it is saying, the question says that there is some node in the list, there is some node in the list that can be reached again by continuously following the next pointer, which means that it is possible that this node comes back and points to this. Okay, so if you are here, you go to the next pointer, you reach here, and then you reach here, and then you reach here, and from this node, suppose this is 3, 2, 6, and 8, from 8 you can go back to 2. Okay, which means there is a cycle. So this is the cycle, and we need to detect if the linked list that is given to us has a cycle or not. I hope the question is very, very clear. Let us look at the examples that are given. So we have an example very similar to what I showed you, and it says there is an input head 3 to 0 and 4, and there is the output is true because there is a cycle here, right? So there is a cycle in the linked list where the tail connects to the first node, 0th index, and we don't have to return where the cycle is. We just need to return a boolean if a cycle exists or not. Now there are follow up questions on this, but right now we are just doing the basic version. And here also we have a cycle, and if there is a single node, then there is no cycle. Okay, so let us take it up and let us try to think of an approach to solve the question. So this is question number 141. This is lead code 141, linked list cycle. So guys, what do you think should be the approach for this? Does anyone have any idea? So suppose we have a linked list like this, 3 to maybe 10, maybe 15, and maybe 20, and then this 20 is pointing back to this 10, suppose. Okay, so if we traverse, do we need to store the values? Otherwise, how do we know the value is repeating? There's no mention about the values. There can be two nodes with the same value. That does not mean that there is a cycle, Sumit. Okay, so let us say that we start iterating. Okay, we take a current pointer on the head. So we will be given the head. The question says that we will have the head, and suppose we start iterating with the current pointer. Okay, and whenever we are iterating, we store that value maybe in a set. So this is something similar to a duplicate, finding duplicates kind of a thing. And if we store the reference of the current, maybe we are on 3, and we store this node 3 here. I'm drawing it with a square uh, around 3, which means that I'm storing the node. Okay, it's not just the value, it's the node, like the pointer to a reference to the actual value, actual node. Okay, and then I take this current pointer and I go to 2 and I check if 2 is existing in my set. So 2 does not exist, so I'll move again and I can have 2 here. Okay, and then I take 10 and I check if 10 is existing in my list set. If 10 is existing, that means 10 has been visited for the second time. That means there has to be a cycle, because the question says that a node can be reached not just in one way but in two ways, and that is possible only if there is a cycle. If there is no cycle, then there is only one way of reaching a node. So we go to 15, right? And then we put 10 here, and then we put 15 here because 15 also does not exist, right? And then you move it again, you go to 20, 20 does not exist, so you add 20. And if you go to the next pointer of 20, you again reach 10, and this loop will continuous. This will be an infinite loop. Okay, we'll go from 10 to 15 to 20, back to 10, again 15 to 20, back to 10. So this will be an infinite loop. So the moment we are at 20 and then we try to move again, we go to this 10 node and we see that this 10 node already exists. Okay, so that means this is the duplicate. There is a duplicate existing. Okay, now what is the time complexity of this? Guys, do you think this is a fair solution? What might be the time complexity of this one? Time complexity is O of n, roughly, and space complexity. Okay, it will be more than O of n, but it is bound to grow linearly. Okay, space complexity is also O of n because you are storing all the nodes here. Okay, skydiving Anil is saying that we save ID of all the linked list and see if the duplicate is. Yes, correct, correct. That is what we are doing. These are references to the nodes. Okay, stores references to the nodes. Okay, mind you, I'm not storing the value because value can be repeated. Okay. So this is one way of doing it, and there is time complexity and space complexity, and both of them are linear. So you can try to write this solution. There is one more approach for this, which is called as a two pointer approach, which we have seen in arrays. And like I told you, two pointer is a very universal technique, which is a very powerful technique, and it's going to be used very often in uh, other data structures also. So we can use a two pointer technique here. Okay, this is also called as slow and fast pointer. I think talked about slow and fast pointer when we were solving the finding middle node of a linked list wala problem. This is also called a slow and fast pointer. Sometimes people will also call it the hare and tortoise approach. And tip and just for this cycle detection, this is also called as a Floyd cycle detection algorithm. These are the different names you will see very often. Okay, so it doesn't matter what it's called, but let us try to uh, understand what is the intuition behind it. Okay, so suppose if we have a linked list and there is a cycle existing here. Okay, and if we take a slow and a fast pointer, suppose we take one pointer here, this is called as a slow, and we take one more pointer here, this is called as fast. So if you remember, when we were doing binary search, there also we were taking two pointers, and we used to call them left and right, and or low and high. If you talk about sliding window, we were using two pointers, and we used to call it left and right. The two pointers defined the length of the window. Here again we are having two pointers. It doesn't matter much what you name them, but intuitively they are called as slow and fast because that is the behavior. And basically what happens in a slow and fast pointer is that we move the slow pointer one step. Okay, and the fast pointer moves two steps, one and two. Okay, and we again move the slow pointer one step, and we move the fast pointer two steps, one and two. Okay, and then again we move the slow pointer one step, and we move the fast pointer two steps. Let me draw it in a different way. Okay, so imagine if there is no loop here, then what's going to happen? We have moved fast pointer two steps and slow pointer. Let me start again. Okay, so the slow pointer will move one step, and the fast pointer will move one and two. Slow pointer will move one step, and fast pointer will move one and two. Slow pointer will move one step again, and fast pointer will move one and two. Okay, so fast pointer has reached the null. Okay, so this is basically none. So if the fast pointer has reached none, then definitely there is no loop. We are going to return false. I hope this is pretty clear to all of you. If you have learned about linked list, you know that this is something that we do very commonly. We iterate the linked list, we traverse the linked list, and if the pointer reaches the end, that means it's a normal linked list. That is how it is supposed to behave. But in case there is a loop, in case there is a circle here, in case there is a loop here like this, then what's going to happen? Let me bring the slow and fast pointer again back to where we started. Again, the slow pointer will move one step, and fast pointer will move one and two. Okay, and slow pointer will move one step, and fast pointer will move one and two. Slow pointer will move one step, and fast pointer will move one and then back to here. Okay, I hope you guys are following what I'm showing you. Okay, and again the slow pointer will move one step. Okay, and fast pointer will move one and two. You see what has happened? Slow has become equal to fast when there is a loop, and this is going to happen. There is a mathematical proof for it, but we can think of it even if we don't know the mathematical proof. Intuitively, it makes sense that if they are running in a loop, eventually they are going to join at some point. They're going to land on the same node at some point. And if the slow pointer and fast pointer becomes they merge at a certain point, if they become equal, if they are pointing to the same node, that means there is a loop. Okay, so what's the logic? What is the logic here? If fast becomes none, okay, that means no loop. So we return false. Okay. And if slow and fast, okay, converge, not converge is not the right word. If the slow and fast pointers meet, then there is a loop. Okay. And they are bound to meet at some point. Okay. So this is the Floyd cycle detection algorithm. This solution is going to work um, in linear time complexity. So the time complexity for this is O of n, but space complexity compared to the earlier approach that we saw is better, and we are not using any extra space. That's why space complexity is O of 1. Guys, did you follow the approach and the solution and the intuition? Let me know in the chat, please. Should we write the solution for this? Let us try and write the solution for this one. Okay. So what are we going to do? We are going to start. Let me write down the approach using Floyd cycle detection using slow and fast pointers. Okay. So what's the first step? Initialize the slow and fast on head. Okay. So I'll say slow and fast both are pointing to head. Okay. And then I'm going to say while fast and fast dot next. Okay. Why I'm saying fast and fast dot next? Try to think on it. Otherwise, I'll give you a dry run when once I write this code. But very obviously, when are we going to iterate? When are we going to finish this loop? Okay. Either when the fast becomes none, okay, or fast dot next becomes none. Why these are the cases? Why these are the two cases? Suppose I have two linked list. One is having 1, 2, 3, and 4 nodes, and the other is having 1, 2, 3, 4, and 5 nodes. Okay. So if the fast pointer is here and if it is jumping, okay, we'll have fast dot next, fast dot next, fast dot, sorry, it will jump two times. So when it jumps first time, it is going to come here. Okay. And fast is here, and fast dot next, uh fast is not none, and fast dot next is also not none. So we are going to jump and we are going to bring it here. So once it comes here, it becomes none. That is when we are going to terminate the loop. This is case of even number of nodes. And if we talk about the odd number of nodes, then again, if you do a dry run, we do fast dot next. Fast will take two steps, so it is going to come here, and again it is going to come here. Okay, and again we want to make it jump. Okay, so again if it jumps, it is going to come here. Okay, fast, sorry, if it comes here, then fast dot next is not present. So we cannot do fast dot next. It cannot jump two times. It cannot jump two times here. Okay, so that's why this is the end. So we need to check that fast and fast dot next. Fast dot next will correspond to odd number and fast will correspond to even number. And I have explained this logic when we were talking about finding middle of the linked list. Okay, I hope you got an idea. We'll say while fast and fast dot next. Okay, we will move the slow pointer by one step. So we'll say slow is equal to slow dot next. This is moving the slow pointer by one step. and we'll say fast is equal to fast dot next. So this moves the fast pointer 2 steps. Okay. Now we'll say if slow has become equal to fast, and this will happen, this will happen when there is a cycle. If there is a cycle, at some point slow and fast are going to meet. So when they are going to meet, we will return true. Okay. If if this case is not true, if there is no cycle, then definitely this loop will break at some point. Either fast will become none or fast dot next will become none. In such a case, we will just return false. Okay. So I hope you got the solution. Let me run this. Hopefully it will work. Let me check the comments. Guys, are you following? So let me submit this. Okay, seems to be working. Let me take this question and add it to our collab document so that you will be able to revise it. Okay, and guys, please try to solve the other one on your own, the other approach that I showed you using a set. Please try to do it on your own. Okay, so this is the solution. You can check it out in the collab document. The link to this collab document will be in the description, and the link to the sheet, the DSA sheet, is also in the comments. Guys, should we do another one? Let me mark this one as done. Okay, let us do another question, which is which one should we do? Let us do duplicates wala. Question number 83. Guys, please tell me in the chat if you're following. Can we move ahead? Let us read the question. Question number 83. Remove duplicates from the sorted list. Let us do this one. I've also not solved this question. First time I'm also seeing. Okay. Let us read it and try to understand and come up with an approach. The question says that we need to remove duplicates from a sorted list. Okay. So sorted list, remove duplicates from so it says given the head of a sorted linked list, given the head of a sorted linked list. Okay, sorted linked list, we have seen sorted linked list will mean that all the values are in sorted ascending order or descending order. By sorted, by default we'll assume it is sorted. Delete all duplicates such that each element appears only once. Return the linked list sorted as well. Okay, so we need to return a version of the linked list that is not containing the duplicate nodes. So if we have one and then one and then two, we need to somehow delete the duplicate one. We need to delete this node and we need to return 1 and 2. Okay, let us see if there is any other example. Fine, there's one more example. You can see the example has 1 1 2 3 and 3, and it is deleting this node and it is deleting this node, and it is giving us 1 directly tied to 2 and 2 is directly tied to 3. This is the answer that we are getting, and we are returning the linked list after deleting these elements. So I hope the question is clear, guys. Let us try to come up with an approach. This is question number 83, remove duplicates from a sorted list. Can someone tell me a possible approach for this? I'm also thinking. Let me take some example. Suppose this is 1, this is 1, this is 2, and this is 3, and then this is 3. Guys, tell me, what can we do? Anyone? What I'm thinking is that if we are at any node, okay, because it is sorted, because it is sorted, so duplicates are always going to be together, okay, and this property you are going to use very often, even when you are trying to remove duplicates from any array, which is a very common pattern in a question where you have a array which is sorted and which has some duplicates and we want to do something with it, okay. So it's a very common pattern, and it's a very common property that if it is sorted, then all the duplicates are going to be in one place, okay. So if my current pointer is here, I'm just thinking out loud, you guys can correct me if I'm wrong. If my current pointer is pointing to this node, and if I have a duplicate, then the duplicate is going to be current dot next, okay. So if the duplicate is current dot next, then I'm simply going to connect, then I'm simply going to point the next pointer of my current, okay, to current dot next, okay, and I'll remove this connection. If my current dot val, okay, if my current dot val is equal to, if my current dot data is equal to current dot next dot data, okay, if this is the case, okay, then I can simply say that my current dot next is equal to current dot next dot next, okay. We can take a set for this, and if it is in scene, then append. uh, you will have to create a new list for that. The question does not say that you have to create a new list. You have to remove the duplicates in the given list. AI wala bro. Okay. If I have read the question correctly, I'll just read it again and maybe I'll see. Okay. And if this is not the case, if this is not the case, then we'll just move the current pointer to the next pointer. Else, we will just move the current pointer to the next pointer. Current is equal to current dot next. Okay. And once this is done, then we will just return the head. Okay. And there will be a loop here. And let me do a dry run. But I hope you got the approach that I tried to, I'm trying to show you here. I'll say while current, should it be current or current and current dot next? Current will come, okay, so we will be here, current will come here, okay, and then again the loop will run, current dot data is not there, they are not equal, so it will come here. If it is, now 3 and 3 are again none, so current will become current dot, this connection will be removed, this connection will be removed, and it will become current dot next will become current dot next dot next. So next dot next is none. So this will become none. So if you redraw it, it is going to become 1, 2, 3, and 3 is pointing to none. So this becomes our answer. If 3 duplicate are continuous, then this logic will fail. Why? I did a dry run. Why will it fail? As long as current dot, as long as the current dot data is current dot next dot data, you will jump one. After 2 again, if there is one more 2, then again this statement will be executed. Basically what I'm saying is that if your next node is having the same value, then skip that node. Basically delete that node and move the pointer to next node. So this is basically the code for deleting a node. Okay, and that same logic will again apply. If after 2 again there is a 2, suppose there was one more 2 here, again that would have been skipped and it would have gone to 3. Okay, let us try it out and see. So what I'm saying is that I will start with start the current on the head. Okay, so I'll say current is equal to head. Okay, and then I will say while current. Uh, so did I decide whether it will be current and current dot next? Let us keep that point here. Okay, current dot next also should be there or not. Let me see. Okay, but if current dot data, it's not data, it is val. Okay, fine. If current dot val is equal to current dot next dot val, which means there is a duplicate next. Okay, so then what we are going to do, we are just going to short the connection, and we are going to say current dot next is equal to current dot next dot next. Okay, if that is not the case, then simply we will move the current pointer. We'll say current is equal to current dot next, and we'll return head, because after this is done, the head is where it was supposed to be, and it will move ahead. Now, should it be current or current and current dot next? That's what I'm confused. Let me just do one more dry run. Okay, so if current and current dot next, so current will come here. Okay, current dot next should be present, otherwise it's not going to go anywhere, right? So it should be, we need to have current and current dot next. Let me run this. Yes, it's working. Did you guys understand why I am saying current and current dot next? Because if there is no node after current, then there is nothing to compare, right? That means it is the last node. So yes, this is working fine. I did not see this question earlier. Solved it just now. Uh, okay, let me take this one and put it in the collab. Let's do one more dry run in case it is not clear. Let us take one more example from the same question. Let me create one question on my own. Let's say that we are having 1 and then 1 and then 2 and then 2 and then 2 and then 3 and then 3. Suppose this is the linked list that has been given to us. Okay, and what was our code? Let us go line by line on this code. Okay, so this is the code. Let us do a dry run. So we'll say that our current is at head. So this is our head. Fine. And while current and current dot next, so current is present and current dot next is present, that is the case. So we'll go and check here. Okay, that if current dot val is equal to current dot next dot val, so these values are clear, these values are connected, these values are same, 1 and 1. So it says current dot next is equal to current dot next dot next. Okay, so we are going to make this connection here. Okay, and if we make this connection, then this connection is gone. Okay, and then we are going to again go and say while current and current dot next. Okay, if current dot val is equal to current dot next dot val, so current dot next dot val, that's this connection is not this case is not valid now, so we'll move the current pointer ahead. So current pointer is going to become current is equal to current dot next. So we are here at 2. Okay, again we will run the loop, and it says if current dot val is equal to current dot next dot val, we are going to say current dot next is equal to current dot next dot next. So again we will take this connection and we are going to put it here. Once we do that, then this connection is lost. Okay, and again we will come back and again we are going to check if current dot val is equal to current dot next dot val. So this is my current and this is my current dot next. So again they are equal, right? So again we will do current dot next is equal to current dot next dot next. So current dot next, and this is current, this is current, this is current dot next, and this is current dot next dot next. I hope you are getting what I'm saying. Okay, so we'll again break this connection and we are actually going to make this connection. Okay, and again we will come back, and this next time this connection will, this case will not be valid. We'll come here and it will say current is equal to current dot next. So we'll bring this here and we'll delete this, and current will become current dot next. So current dot next is this, right? And I hope this loop will run again. So I hope skydiving, Anil, your question is answered. What if there are 3 duplicates are continuous? Then this logic will not fail actually. Okay, so we are again here and it says if current dot val is equal to current dot next dot val, current dot next is equal to current dot next dot next. Again this condition is valid, so we will make this connection here like this, and once we do that, then this is lost. Okay, and again we will come and we will move this connection, this condition will not be valid. We will come to this condition, current is equal to current dot next. So we'll say current is equal to current dot next. So we will come here. Once we come here, then current has become null. So this loop will terminate. ये वाला loop will terminate. So once this loop terminates, our code is finished and we will return head. So our head was here. So our head now has 1, and then it has 2, and then it has 3, and then it has none. So this was the expected answer. I hope this is clear, guys. I've done a line by line dry run on this. I'll take 2 minutes. If anyone has any question, please tell me. Let me mark this question as done. Let us do one more question and then we'll call it a day. Let us do a very common question. Uh, let us do question number 19. This question was asked in a interview very recently in a FANG company. So it's a medium question. Let us try to do this. Guys, please take a moment to read the question. What should be the intuition for this? Let us read the question and try to understand it. The question says that we need to remove the nth node from the end of the list. Okay, fine. So given the head of a linked list, remove the nth node from the end of the list and return its head. Fine. So let us see the example. The example says that we have 1, 2, 3, 4, and 5. Fine. And we will be given a value of n. So the value of n is 2. So the value of n is 2 means that we need to remove the second element from the end. Remove nth node from the end of the list. So we need to remove this node. And then we need to return what? We need to return the linked list like this 1, 2, 3, and 5. This is the answer that is expected from us. Is the question clear, guys? And we can look at the constraints. So the number of nodes in the list is SZ. I don't know what that means. Okay. Size maybe, and size is between 1 to 30, not very important. Node dot value can be 0 to 100, not very important. The value of the nodes can be between 1 to okay, the value of n, which means the number of the position of the node that we want to delete can be between 1 to sz. Fine, that is fine. And there's a follow-up question that can we do it in one pass? Okay, so what is follow-up is something that we can reserve for later. But what is the first approach that comes to our mind? Question number 19: remove nth node from the end of the list. Let us try to figure out an approach. Anyone has any questions? Saif is saying that we can iterate the pointer to position -1 and then they make the position pointer next to next. Fine. We need to traverse till the end of the linked list and then find the position to be removed. If you traverse till the end of the linked list, then how will that help? Saif, what you are saying is pretty valid. Okay. So this is basically from the implementation of linked list that we did in class, right? Where we delete from any position basically, right? Except that the value of n is from the end. Value of end is from the end. Usually when we did the implementation of linked list, we talked about adding a method called remove, where we give a position and we are removing that node, but that position is from the left side. This time it is given from the right side, right? So if we know the size of the list, then it is pretty obvious how we have to do that. So let us look at that solution, and then there's a follow-up question that can we do it in one pass? So if we do it this way, we have to take two passes, right? And I think we were doing one question where I talked about this two pass and one pass, right? I think middle of the linked list when we were solving, I told you about that. So suppose we are having this linked list 1, 2, 3, 4, 5, 6, 7. Suppose, okay, and suppose this is the node that we want to delete. So suppose value of n is 3. So what we can do is we can start from the current pointer here. I'm just giving you the approaches. We'll not write code for all of them, but from how much we have discussed about linked list, this should be little intuitive, that we can take the current pointer here and we can iterate till the end, and we'll find uh, that the size of the linked list is 7. right? And then the value that has been given is 3. That means we have to delete the fourth node. Okay, so we are 0, 1, 2, 3, 4. So basically it becomes a question of deleting the fourth node in the node at the position 4 in our linked list. So we know what we need to do. We need to iterate till position -1. We can come till here. Okay, and we can just say that current dot next is equal to current dot next, right? We can do this. This code you have written, guys, I'll give you let me see if I have it handy. This is the implementation of linked list that we did in class, and we talked about um, somewhere it should be. mm, okay, we did not write the entire code. Let me look on my GitHub. I don't want to write that code again. I just want to show you. You can refer it later, and then we'll look at another approach to answer the follow-up question. Okay. So guys, you can check out this notebook where we have done implementation of linked list from complete scratch. And you can see we have written a method here, which is delete from beginning, delete from end, and delete at any position. So basically in a linked list, if you want to delete a node from any position, then what we need to do, and these checks are there. These are general checks, but in our case, these are not going to be valid. So basically we are going to iterate to the position before the position that we want to delete. So we want to iterate, we want to reach the node just before the node that is supposed to be deleted, and we'll do current dot next is equal to current dot next dot next. That is what I have written here. Current dot next will be current dot next dot next. This approach should be very, very clear to you. But how many passes this is taking? This is taking 2 passes. The brute force is clear to you guys. Again, I'm repeating what we are supposed to do. If we want to delete this node, if we want to delete this node number 5, then we will start from the head and we will come till the node which is just before the node that is supposed to be deleted, and then we will do current dot next is equal to current dot next, which will basically do this. It will take this connection and it will join here and it will delete this node. That is what will happen. Now what is another approach to do this? We can use a two pointer approach. We can use a two pointer approach. How that will work? 1, 2, 3, 4, 5, 6, and suppose I have 7 nodes. Okay, and suppose this is the node that is supposed to be deleted. Suppose n is equal to 3. So I'll put one pointer here, okay, and another pointer here. 2 pointers. I will start with 2 pointers. I'm just giving you the intuition. If we move, suppose this is the left, I'm calling it, suppose this is my left pointer and this is my right pointer. Okay. If I move my right pointer by 3 steps, 1, 2, 3. Okay. Suppose I do this. And once I do this, I create a gap of 3 nodes. Okay. And then I start iterating them together. So then I move left 1 point and I move the right 1 point. Then I move left by 1 point and I move right by 1 point. Then I move my left by 1 point and I move my right by 1 point. Okay. Then again I move my left by 1 point and I move right by 1 point. Okay. Can you see that the moment right pointer becomes none, when the right pointer becomes none, the left pointer is pointing to the node that is supposed to be deleted. Basically, we wanted to find out which node is supposed to be deleted. And in order to do that, we were first finding the size And once we find the size, then we were find once we find the size, from there we were deducing which node is supposed to be deleted. Correct? And that was taking two passes. We were making two passes. The follow up question is that can we do it in one pass? I hope this approach is clear, guys. Okay, I hope this approach is clear. If this approach is clear, you will be very very convinced that this is taking two passes. The follow up is can you do it in one pass? So what I'm suggesting here is that we create a gap of n between left and right, and then we iterate left and right by one steps. Okay, so if n is equal to 3, I am proposing that we move the right pointer by 3. 1 2 3. 1 2 3. How do we know that many steps we need to move to right? The number of steps, that is the value of n. Value of n is 3. ठीक है? तो वैल्यू अगर n का वैल्यू 3 है और 3 का अगर गैप हमने बना दिया यहाँ पे, ठीक है, 3 का अगर गैप बना दिया, 3 का अगर गैप बना दिया, इसका मतलब जब ये राइट पॉइंटर, इसका मतलब जब ये राइट पॉइंटर एंड पे होगा, जब अगर 3 का गैप है तो जब ये राइट पॉइंटर एंड पे होगा तो लेफ्ट पॉइंटर उससे 3 पीछे होगा। और वही तो नोड हमें डिलीट करना है, वो नोड जो लास्ट से 3 पीछे हो। ओके, अब ये 3, फाइन, इफ यू आर सेइंग दैट ओके सर दिस इज 3 व्हिच मींस दिस शुड बी 1 2 3 should be here, fine, that is not a problem. That is just indexing how you are counting, that is fine. Priyanka is saying why are we taking the right pointer out of linked list? Left should be pointing 1 before the node which needs to be deleted. See, that you can manage, that is fine. That is fine. You can do n minus 1, that is fine. But is the high level logic clear what we are trying to do? Basically we are trying to create a gap of that many nodes between left and right, and then we are making the right pointer go till the end. If the right pointer goes till the end, then the left pointer is pointing n steps behind that. So this entire trick is to find out, is to reach the node to be deleted in one pass. Is this approach clear, guys? Take a moment to visualize it, or if you want to take a pen and paper and write it down. Can we write the code, guys? Now someone is saying that we should be pointing to the node before the node which needs to be deleted. Okay, so valid point. Mm, hmm. So how to handle that? So see, what we can do here, what we can do here is that two things. There are two ways. So see, high level approach, we are clear what we have to do. We have to create a gap between left and right of that many number of steps. Once that many number of steps ka gap is created, then move both the left and right pointer together till the end. Okay. Now there is a small thing, small technicality which we have discussed earlier also, that if we want to delete a node, we want to reach the node before the node is supposed, before the node which is supposed to be deleted. Okay, not the node which is supposed to be deleted, the node before. Okay, so there are two ways to handle that. Okay, one is a elegant way, one is not very elegant way. So let us think of that thing. So basically we have decided the approach, we are thinking about how are we going to implement it, basically how are we going to write the code for it. So let us discuss that. So suppose this is the situation, and suppose this is the node that we are supposed to, guys, what is the time? 9:58. We'll move fast. Okay, so if we are having our left and right pointer both here, okay, and suppose n is equal to 3, so this is the node we are supposed to delete. And if we take n steps, we can do n minus 1 steps. Suppose we do n minus 1. Suppose if we take 2 steps, okay, and then if we iterate till the end, so this will come here and this will come here, this will come here and this will come here, this will come here and this will come here. Okay, when the right pointer goes to the null, then this is not pointing to the correct node. Okay, it is pointing afterwards. Okay, what you can do here is, the non-elegant way is that you can create a third pointer to track. We will move 3 steps only. We'll move 3 steps. Okay, 1, 2, and 3. We'll move 3 steps, and then this will come here. This will come here. This will come here. This will come here. This will come here, and this will come here. Okay, so this is solving our problem, except that the left pointer, this wala pointer, is at the node which we are deleting. It is not at the node before that. So what you can do is you can keep track of a previous node. If you remember the solution of reversing a linked list, you can use a previous node concept. Okay, where you can keep track of the previous node here like this. Okay, think about that, how we can do that. But I will propose another approach which is slightly more elegant. Okay, so basically what you will do here is, when you will move the left pointer, you will keep one previous pointer which will be just behind the left pointer. This is one way. I will discuss this approach later, but I will propose another approach where we will create a dummy node. If you remember, we were doing the merged sorted list. There I talked about the importance of dummy node in linked list solving problems to reduce the number of lines of code that we write. It is not more efficient, it is just reducing the number of lines of code. So what we can do here is we can create one dummy node, and that dummy node can be before the head. Okay, and if you start from here, I think that should solve the problem. If you start from here, and then if you create 1, 2, 3, okay, and then if you jump 1, and then if you jump here, you jump here, you jump here, you jump here, and you jump here, and you jump here. Sorry, what happened? I made a mistake. Let me see again. You take 3 steps, 1, 2, 3, okay, and then this comes here, 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 and this comes here. Mm, yeah, and this comes here, and this comes here. Okay, so we are deleting the third node, right? So this will solve our problem. Basically, we will create one dummy node before Okay, so that when we create a gap, we are creating one extra dummy node, so that when we create that gap, we don't reach. Okay, again we are reaching the node which we are deleting. No, uh, we can create dummy node 1 and 2. Suppose if we create just two gaps, then what happens? Just give me a moment, guys. I also have to figure it out. Uh, here, 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 here. If we create two, let me see. I'm getting confused. We create. I don't want to do it with the previous pointer. I'm wondering. mm, we take n number of steps. Right is equal to if 2. So 0, 1, and 2. Three steps we have taken. Mm, if we move this, move this, move this, move this, move this, and move this, while right. Okay. Okay, fine, got it. You have to move n plus 1 steps. We'll have to move not n steps. We have to move n plus 1 step. A little bit of hit and trial. Okay, now I got it. Okay. Silly thing, but what we'll do is we will move it n plus 1 steps. Now you will ask why n plus 1 steps, because I tried multiple things and that is what it is. That is what is working. So we'll take one n plus 1 steps, not n steps, but n plus 1 steps. So you see what will happen. If n is equal to 3, we move the right pointer 1, 2, 3, 4. Okay, and then we move it. This comes here, 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 and this comes here. You see where the left pointer is. The left pointer is before. We did all this drama to reach the node before the nth node from it. Okay, I hope you guys got it. Little bit of confusion, but that is how it is. uh, it is still pointing. Okay, Priyanka, we can use elements position minus 1 gap between the pointer. Position plus 1, it turns out position plus 1. So guys, what we will do, I hope it is clear. We'll use a dummy node. I'm explaining it one more time. What we will do, you have this many nodes: 1, 2, 3, 4, 5, 6, 7. Suppose 8 nodes are there, and suppose the n value is 4. Suppose n value is 4, which means 1, 2, 3, 4. Suppose this is the node you are supposed to delete. Or let me take n is equal to 3, or let me take n is equal to 2. Suppose, okay, n is equal to 2, which means this is the node you are supposed to delete. This is the node you are supposed to delete. So what I'm proposing is that we will take one node before and we will call it dummy. Okay, and we will take two pointers, left and right, and we will move the right pointer n plus 1 times, not n times, n plus 1 times. We'll do 1, 2, 3, 3 times, and then we'll move both the pointers together. We'll move this here and this here. We'll move this here and we'll move this here. We'll move this here. We'll move this here. This will come here. This will come here. This will come here. This will come here. And when this goes out of bound, then this comes to the node before the node which was supposed to be deleted. Okay. I hope you guys got it now. Okay. So what we will say, let me write the code. We will start, we'll say we'll create a dummy. We will create a dummy is equal to node. We'll say it is a node with some random value -1, and this node ka jo next pointer hai, it will be head. Fine. Then we will say that my left and my right both are at dummy. Okay. After that, we will move the right pointer n+1 times. Okay. So we'll say for underscore in range n+1, we'll say right is equal to right dot next. Okay. So once this is done, our right pointer is at n distance away. So the distance we have to maintain n. So we have to move n+1 step. It makes sense. Okay. And then we will say while right, okay, we'll say left is equal to left dot next, and right is equal to right dot next. Okay. Once we do this, after this, our left pointer will be left pointer is at um, node before the required node. Okay, required node is nth node from the end. I hope you are getting it. Required node. Okay. So what we will do, we'll simply say left dot next, because if you remember in deleting, the current pointer was before the node which was supposed to be deleted. So we were saying current dot next is equal to current dot next dot next. So we'll say left dot next is equal to left dot next dot next. So this will delete the node after left. Okay. Once this is done, then we will simply return uh, our head. We already have our head, so we'll just return our head. Okay. Now you will ask what might be the edge cases of this. Priyanka is saying there is no need to use dummy. Actually, there is a need to use the dummy because dummy will help you solve some edge cases. Suppose if you are deleting the first node, then dummy is going to help you. Okay. So this is deleting nth node from end in one pass. Okay, it is not necessary to use the dummy, but if you don't use the dummy, then you will have to write more code. It will not be more efficient code, but just that you'll have to write more code. So you can try uh, tracking the previous pointer. Maybe I'll explain that in a different one, but let me now try to just complete this, solve this, and see if what we have written is correct or not. The approach. So I'll go here, and what was the question number? Remove nth node. Okay, so let us do this one. So we'll say we'll create one dummy node. Are we going over time? Oh, it's 10:10. Okay, guys, we'll speed it up. We'll say this is list node. I'll say the value is -1, and the next is head. Okay, or you can do dummy dot next is equal to head. Let me check the chat once more time. Slow pointer applicable in linked list, or is there any DS where it can be used? Slow and fast pointer is usually used in array and linked list, mostly in linked list. Okay, so we'll put left is equal to right is equal to dummy. Okay, then we will say, then we will move the right pointer n+1 steps. Okay, so we'll say for in range n+1, We'll say right is equal to right, sorry, right is equal to right dot next. Okay, so now we move left and right together. So we'll say while right, we'll say right is equal to right dot next, and left is equal to left dot next. Okay, so once this is done, then now our left pointer is before the node to be deleted. Okay, see, if you did not don't use the dummy node, then if you have to delete the first node, then you have to write a edge case for that. But here, because you're at the dummy node, okay, you are before, so even if you want to delete the first node, it becomes convenient, the same logic will work. Okay, take a pen and paper and try to do a dry run for that. Left pointer, so where was I, what I need to do next? Left pointer is before the node to be deleted, so I will say left dot next is equal to left dot next dot next. Okay, so this is done, and then I will return, I'm not, see, I will not return the head, I will return dummy dot next. Okay, so dummy dot next will be none if the first node was supposed to be deleted, because n can be equal to 1 also. The size can be equal to 1 and n can be equal to 1. So suppose there is only one node and that node is supposed to be deleted, in that case you have to write edge cases. I hope we are right. Left is equal to right is equal to dummy, we are moving the right pointer in plus 1 steps, then we move the left and right together, then left dot next. I hope this should work. Please God, let it work. Hmm. What happened? Syntax error. चल गया. चल गया. Guys, did you get it? Do you want one more dry run on this? Just tell me in the chat. I will do that. Otherwise, we'll finish the discussion for today. Let me add this question in the DSA sheet. Sorry, the collab sheet. So guys, for every question, I have told you two approaches, but I have written the code only for one approach. So the other approach, please write it on your own. And try to run that code and be very clear in your mind which one is more efficient and for what reason. Okay, so removing nth node from the list, you will have the two pass approach where you can find the size, then you can deduce the position that is to be deleted, and again iterate one more time, traverse one more time to reach that node and delete it. So that is approach number one, and approach number two is the two pointer approach that I've shown you here. And in this also, try to write it without the dummy node approach. Okay, so in your mind you will be clear as to why we are using dummy, and if we don't use it, why we will have to write more code, although I have shown that to you in another example. If you remember, we were doing this example, right? Ye wala, without dummy node and using dummy node. I have given two code solutions for the same question for merging two sorted list, and you can see here we had to write so much of extra code just for edge cases. To avoid that, we use a dummy node. Okay, that's it for today, guys. We have solved three questions, and check out the DSA sheet and try to solve other questions. Other easy questions that you can attempt is palindrome wala question, and intersection wala question, merging, find the merging point. This also you can do, and reversing a linked list wala question, please revise it. And there are some other questions. It's a mix of easy and medium, so try to do both easy and medium questions. Okay, so that's it, guys. That's all for this live session, and I'll see you again on Thursday. Before we move quickly, I want to, for those of you who are not from my live class, please check out the linked list lecture. Okay, everything that I've shown you today, if that's not making much sense to you in case, then please check out this video. Where is it? Okay, please check out this video. And you can find all the code, all the notes here, and the DSA tracker sheet also. And I've explained everything, each and everything here in a lot of detail, and all the code is here. And there are 3 lead code questions also. These are the questions that I have not solved in today's class. These are separate questions. So all in all, including today's class, you will have 6 lead code questions. If you solve these 6 questions, you will have a good introduction to linked list. Okay, so that's it for today, and I'll see you on Thursday 9 p.m. Bye guys, take care.